At the centre of our Milky Way galaxy, nestled beside a supermassive black hole, lies a group of stars. Everything about these stars seems pretty normal, except for one thing. They shouldn't exist. Thanks to the supermassive black hole that they call their neighbour, the gravity in the area that they reside is so strong that it is supposedly inhospitable to any baby star. And for decades, scientists have been trying to explain why any stars exist there. And so this group of stars has remained a total mystery. Until now. So what do we know about these stars, and where do we think they came from? Hello, welcome to Brain Noises. My name is Chloe, science communicator and recovering physicist, and on this channel we talk about the thoughts that pass through my mind, generally relating to science, but I cannot make any promises. So sit back, relax, grab yourself a cup of tea, and let's talk about the impossible stars at the centre of our galaxy. Thanks for being here. To understand why they shouldn't exist, you need to understand where stars come from, and the life cycle of stars is broadly pretty well understood. All stars ever began as a huge cloud of gas and dust made of mostly hydrogen and helium called a nebula. And when I say huge, I mean huge. Some nebulae are hundreds of thousands of light years in diameter. Anyway, the dust and gases in a nebula are very, very spread out, but gravity can slowly begin to pull together and form clumps of dust and gas. As these clumps get more massive and massive, their gravity gets stronger and stronger, and the cycle continues. So the dust clouds slowly collapse into a number of points known as cores, and at the centre of these cores, which are now incredibly hot, there is lots of very dense material. Eventually, there is such a high pressure and so much heat that a nuclear fusion reaction begins and the star starts to shine. Now, there's a lot more to the life cycle of a star, but for our purposes, for the purposes of this video, we only really need to worry about the beginning. The nebula, that cloud of dust and gas. In the case of the impossible stars, things were looking pretty normal when it was a nebula. The ingredients were there, the dust, the gas. But being next to a supermassive black hole has its consequences. The enormous mass of the supermassive black hole means extremely strong gravity. The gravity is so strong, in fact, that any cloud of dust dense enough to become a star would be immediately disrupted. This process of the dust clumping together, the cores forming, wouldn't be able to happen with the gravity of the supermassive black hole so nearby. So when and how did these dust clouds have the opportunity to collapse into points and eventually become stars in such a brutal gravitational environment? Most historical ideas to explain these stars at the centre of the Milky Way broadly agree that the stars must have formed elsewhere and then slowly moved inwards towards the centre. The main flaw in this theory lies in the orbit of these stars. If they had formed further out and then moved in towards the centre, the stars should likely orbit within the disk of the galaxy, but these stars don't. They actually appear to be misaligned with the galactic disk. Today, scientists from Stony Brook University are pretty sure they've cracked the code, or at least as sure as anyone can be. They believe that a shockwave from another star's death could have given those little stars-to-be a chance to form, despite the supermassive black hole-shaped elephant in the room. Rosalba Perner at Stony Brook University in New York and Avengi Grishin at Monash University in Australia have come up with this idea. When a star wanders too close to a black hole, that star is ripped apart in what is called a tidal disruption event. These events cause huge explosions and sometimes enormous jets with shock waves that propagate through the surrounding dust and gas. We are going to take a very small moment to talk about tidal forces. In astronomy, and you'll see in the linked paper if you choose to read it, the term tidal disruption event is bandied about quite a lot. Tidal forces arise from the difference in a gravitational force on the extremities of an extended object. So it occurs because the gravitational field exerted on one body by another is not constant across its parts. The nearest side is attracted more strongly than the farthest side, just because it's further away and gravity decreases with distance from objects. An extreme result of this phenomenon is the spaghettification of objects, which you've probably heard of. I actually found a really nice little diagram that demonstrates this. The tides are such that at one time, the top, and I'm being very flippant about my language here, when the top and the bottom of the earth are experiencing low tides and the two kind of sides of it are experiencing high tides, In the case of the side closest to the moon, it's because the water on that side is experiencing a stronger gravity from the moon than the Earth, kind of slightly further away from it. And then on the side of the Earth furthest from the moon, you have the kind of inverse of this effect, and the Earth is experiencing stronger gravity as a result of the moon than the water. So you kind of get this bulge effect. Specifically, a tidal disruption event, or TDE, occurs when a star approaches close enough to a supermassive black hole to be pulled apart by the black hole's tidal force, experiencing spaghettification. And you can imagine in the case of little would-be stars, because they're so much less massive than the black hole, the gravitational forces keeping them together are just nowhere near strong enough to overcome the gravitational forces pulling them apart. When the researchers calculated how one of these shock waves would affect the clouds of dust near the galactic centre, they found that it could compress the gas enough for it to hold it together in the region's intense gravity. After the shockwave compressed the gas by a factor of tens or even hundreds of millions, it would only be a matter of time before those clumps started to become stars, says Perner, speaking to New Scientist. We know that explosive events have a feedback effect on star formation in other contexts. As we were looking into the details of it here, all the numbers in terms of rates, energetics, scale lengths, they all just fell into place. TDEs with jets near the galactic centre are supposed to occur on average one every few million years. And this is similar to the age of those stars, which is encouraging. And the shockwaves would not necessarily be aligned with the disk of the galaxy, which is kind of further evidence. So the stars being outside of the disk does actually check out, as do the masses of the stars. They match the kind of calculations based on what stars would exist as a result of this mechanism. Detailed simulations should help researchers determine whether the strange stars at the centre of our galaxy really do come from the shredding of less lucky stars, Perner says. A little bit earlier this year, something even more curious, to me at least, was found, except this time a little bit further afield. As we've established, supermassive black holes, which lie at the centres of large galaxies like our very own Milky Way, are generally known for causing a lot of issues when it comes to nearby star production. But in January this year, new Hubble Space Telescope observations found that a supermassive black hole in the centre of dwarf galaxy Henneis 210 was in fact catalyzing huge amounts of star formation, so much so that many have described it as a firestorm of star formation. The observations made by researchers at Montana State University were described in a paper published in Nature. The black hole is actually aiding the creation of stars rather than just gobbling them up, says NASA. Speaking to Forbes, Zachary Shute, the paper's lead author, said, "These are the first observations of star formation being triggered by an outflow from a supermassive black hole in a dwarf galaxy. This phenomenon has been observed in larger galaxies, but until our work, it was unknown if outflows from the supermassive black holes could cause star formation in lower mass dwarf galaxies." Hubble has provided a very clear picture between the black hole and a neighbouring star-forming region located 230 light-years from the black hole, says Amy Raines, the paper's co-author. Hubble's amazing resolution clearly shows a corkscrew-like pattern in the velocities of the gas, which we can fit to the model of a wobbling outflow from a black hole. The thing is, in larger galaxies, the opposite thing happens, as magnetic fields sweep away material falling towards a black hole, which then results in blazing jets of plasma moving close to the speed of light, and any gas clouds in the path of those jets would become so hot that they wouldn't be able to cool back down enough to become stars. In the case of this dwarf galaxy, though, its central black hole has a much gentler outflow, so there is just enough compression to precipitate new star formation. Pretty cool, because studying such small dwarf galaxies could really help us understand how supermassive black holes came to be in the first place. Also, as I mentioned earlier, these images came from Hubble, but obviously the more recent James Webb Space Telescope is expected to uncover a lot more about supermassive black holes. For example, and this is my final point because I need to wrap up, one of the most confusing observations that we see in astrophysics is that we see supermassive black holes that were already billions of solar masses when the universe itself was well under 1 billion years old. So it implies even with ridiculous growth, they would have needed to have started as massive as thousands of suns. But like, how? Is the question. With the JWST, we're hoping to answer this question. There's also a lot around like the most supermassive black holes are found in the most massive galaxies, but which came first? It's the ultimate chicken or egg scenario. But yeah, the JWST's infrared observations should really help us out with answering a few of these questions, and I'm pretty excited to see more images come out. Okay, my feet are numb now, but they behave themselves until the very end of the video, so we've got to be #grateful for that. Thank you for watching. As per usual, leave your comments and queries and observations in the comments section, and follow me if you want more. Like the video if you liked the video. See you in the next one. Goodbye.